Thank you, Wendy, and good morning, everyone. My name is Eric Stafford, and on behalf of Anderson Windows, thank you for joining us on the webinar. Welcome you, and thanks to AIA Florida for giving us this platform here. What we're going to talk about today is the Florida Building Code, obviously, but specifically about wind loads. And there's been a couple of subtle changes to how we can determine what our design wind speed is in the code, and that kind of leads into the last part of this discussion on this new tool that Anderson has developed. It's a window and door design wind pressure calculator that I'm going to show you. It's a free tool. We'll go through an example and we'll kind of talk through it a little bit. Makes life a lot easier than using some of these big tables. So I'm going to turn the video off just so we can preserve bandwidth. But also, I normally like to take questions during the presentation, but my understanding is there's close to 1,000 people signed up for this webinar. So we should have some time towards the end of the presentation to take a few questions and can answer them verbally, but I'll also stick around afterwards if you put some questions in the Q&A and answer some of the questions. So, but we'll try to make sure we have some time towards the end. Why is this not advancing? There we go. Not sure what the hang up there was. So let's talk briefly about the Florida Building Code, where we are right now. The edition we're on is the 8th edition, or 2023 version edition. Its effective date was December 31, 2023. So essentially it's been in effect all of this year. One important thing to note about the Florida Building Code now, not just this edition, but the previous edition and the future editions, unless things change, they are not based on the international codes anymore, and in general are moving further away in a lot of cases. So when you see, the wind provisions have largely been kept similar or close to what's in the international codes, but you'll see some divergence on many other areas of the code, particularly chapters 6, 7, and 8, and 9 of the building code, and then also some of the prescriptive chapters of the residential code. Because of the way Florida does it now, they don't adopt the next edition, available edition of the international code. They look at all the changes that were submitted for a previous cycle and decide which ones to include and which ones not to include. Okay, so it includes a lot of the updates from the 2021 international codes, and also includes some updates from the 2024 international codes. The key update is the update to ASCE 7 to the 2022 edition in the 8th edition. And I'll note that the 2021 I codes are still using ASCE 716. The 2024 I codes have been updated to 722, but Florida, being a hurricane-prone state like it is, and wind loads being important, they've already adopted the 2022 edition of ASCE 7. Okay, some of the things we're going to talk about. We'll talk a little bit about changes to the wind speed maps. There's been some minor changes in Florida, some changes in some other areas of the country. And I want to touch on this change to the windborne debris region. I describe it more as it was a change to the windborne debris region. And we'll talk about what happened and kind of where we are now, because this was a pretty big change to the code, and we've now reverted back to where we were. But we will get into the specifics of that. A little bit about changes to the design pressures for roofs on steep slope roof buildings. This was one of the major issues with adoption of ASCE 716. The design roof pressures were significantly higher in ASCE 716 than ASCE 710, and those have been modified a bit, a little bit lower for some cases than they were in ASCE 716, and we'll touch briefly on those. Another big topic regarding wind is tornado loads. We'll talk about the new tornado provisions, the references in the in the Florida Building Code, and then specifically what's in ASCE 7 regarding tornado loads, because this is brand new. We've never dealt with tornadoes before, and now we have to at least consider it. And then lastly, like I mentioned, I want to talk about this window and door design pressure calculator. And this is a free tool that we'll get into, show you how to use it, makes things really, really simple. It's a really slick tool for getting design wind pressures on windows and doors, okay? All right. There we go. So let's talk about the wind speed maps. All of the wind speed maps have been updated based on improvements to the hurricane hazard and wind field models. The hurricane wind speeds have been slightly revised in some areas, including the state of Florida, but no major changes to the wind speed maps. And I'll show you where they have changed in Florida, specifically on some figures. But just for your information, because there's probably a lot of people in other areas that do work in other areas of the country, there's been slight decreases in Louisiana, increases in Texas, and slight decreases in Mississippi and Alabama. And as far as the East Coast goes, Carolinas are pretty much staying the same, and some decreases up in the Northeast as well. Okay. All right. So let's take a look. Let me get these marks off of here. I think this is what's causing the problem, is trying to annotate this screen and it's not wanting to cooperate. Okay. So let's take a look here at risk category 2 map. This is our, most buildings fall under risk category 2, cover single family dwellings, office buildings. So default risk category. If you don't qualify as a risk category 3, 4, or 1 building, then you default to risk category 3. So one of the things you'll notice, you'll look looking at the wind speeds, especially looking at the southern part of Florida, things look very similar to what they were before. Over in the Panhandle, though, things look a little bit different, right? In this area right here, things look a little bit different than they did before. And we'll look at a close-up of that in a few minutes. So that was risk category 2. So now if we look at risk category 3, kind of the same thing. Wind speeds throughout the peninsula look very similar to what we had before. Up in the Panhandle, things look a little bit differently. Same thing for risk category 4. While we're not specifically going into these details, but we know risk category 4 buildings are ones that we expect to remain operational after event. So wind speeds are going to be a little bit higher. But again, we see slight differences there in the Panhandle. And risk category 1, kind of the same thing. So the net effects of these changes to the wind speed maps are, for Florida, is that wind speeds have increased in the Panhandle. The remainder of the peninsula is unchanged from the 7th edition. In fact, when you get eastward of the Big Bend area and south in Florida, wind speeds haven't changed since the 2010 Florida Building Code. They're essentially unchanged, aside from the fact we introduced the risk category 4 map in ASCE 716, but for risk category 2, risk category 3, and risk category 1 buildings, wind speeds are exactly the same. Where they have changed is like I mentioned, in the Panhandle. This green area that I've gotten shown on this map here shows where the wind speeds have increased. This graphic here is an overlay of the risk category 2 wind speed map for ASCE 722 overlaid onto the map for ASCE 716. The red dash contours are the ASCE 716 contour lines, and the black contours are the ASCE 722 contour lines. So you can see in the Panhandle area, wind speeds have increased slightly. Now, with the windborne debris region being triggered by 140 miles per hour, we can see that some areas, because it affected wind speeds in those areas, some areas that previously weren't in a windborne debris region are now going to be. Okay, but again, not a major change, but the rest of the peninsula, no change at all. And you see similar increases like this for other areas. Like I said, some slight decreases in Louisiana, Mississippi, and increases in Texas. But overall, overall tweaks to the wind speed map. And for the interior of the country too, there were some slight adjustments, but no major changes in how we determine wind speed. One of the more, like I said, this is probably a subtle change, but it's really important in terms of how we determine what our design wind speeds are. There's been a couple of tools out there available for a number of years now. I think the one that people are most familiar with is the ATC hazard by location tool. Most of you have probably seen it or used it. And you can go to that site. It's a free site as well. You put in an address or coordinates, and it'll give you a site-specific wind speed. Our experience has been that most jurisdictions are allowing it to be used, except for those that have define like Miami-Dade and Broward counties in Florida. They assign a single wind speed for the entire counties. Outside of there. That area, most jurisdictions are allowing the use of some type of wind speed database to determine site-specific wind speeds. So the change to the code is that now the code specifically permits and recognizes the use of these databases. Now, it doesn't recognize the ATC site, but a new Note 6, as you can see here, has been added to the wind speed maps in the Florida Building Code building and the residential code that permits the use of the ASCE 7 hazard tool, okay? So one of the reasons it only recognizes the use of the hazard tool is that the ATC hazard by location website, which is the one most everybody is familiar with, it will not be updated for ASCE 722. It'll still give you wind speeds for ASCE 716, ASCE 710, 05. I think it goes all the way back to ASCE 793. But it will not be updated for 722. It's going to remain operational. But for Florida and for other states that have or other areas that have adopted the 2024 international codes and are using ASCE 722, you're going to have to use the hazard tool or an equivalent. And I'll talk about that equivalent when I talk about that new design pressure calculator that Anderson has developed, okay? So the language in the notes specifically says you can use the hazard tool or equivalent. So my experience in teaching many of these classes or over the last couple of years is not as many people are familiar with the hazard tool. So we're going to run through a kind of a quick tutorial on how it works, and it works very similar to the ATC site, although it looks a little bit different and gives you the outputs a little bit different, but very similar. So you can Google ASCE 7 hazard tool or put ASCE 7 hazard tool online, and you'll come to this site here where you'll have the opportunity to put in an address or coordinates or find a spot on the map. And then once you find that location, then you have a couple of options. You'll have to, through the scroll down menus, have to pick what version of ASCE 7 you're going to use. Okay, for this example here in the screenshot, I'm using ASCE 722, but you could pull from ASCE 716 or ASCE 710. But the hazard tool will not give you ASCE 705 and earlier design wind speeds, only ASCE 710, 16, and 22. Okay, so you pick the standard version you're interested in, and then pick the risk category the information you're looking for, and then you pick what information you're looking for, whether it be wind, ice, rain, tsunami, seismic, snow, flood, or tornado. It will give you some of the data that you need to determine what the loads are on buildings for the various perils. For wind, it's going to give you your design wind speed. Okay, so for this example, I put in Mexico Beach, and I want ASCE 722 wind speeds for risk category 2, and I click on the wind speed box, and then I click determine, and I'm given the wind speed. It's down here on the lower right corner. I don't know why I like to use this annotate tool, but every time I do, it's not letting me advance the slides. But any rate, so that's where it'll give you your wind speed for that particular condition. Risk category 2 for that specific location. Okay. Now I will note that they do the wind speeds in the hazard tool do differ a little bit from the ATC site, but only by a mile per hour at the most, and that has to do with the algorithm that's used to determine the wind speeds. Okay, so the contours are geocoded, and the hazard tool and ATC site each have a different algorithm that does the interpolation between the wind speeds. So you'll get slightly different wind speeds from time to time, but the differences are very, very minor. And then you can click on, there's an overlay tool. You can look at where you're at on the specific wind speed map, and then you can also get wind speeds for other return intervals if you're dealing with serviceability issues. Okay, so that's the hazard tool. Again, it's free site. Just Google ASCE 7 hazard tool, or type in the URL. Okay, so there are no changes to the exposure categories, but I do want to talk about them a little bit because this comes up a lot. It comes up quite a bit, and it's going to be important to the discussion about the windborne debris region change. And exposure categories are important because they directly affect what your design pressure is. Okay, and I'll show you an example here in a few minutes. But basically, these exposure categories, they're an approximation of the roughness of the Earth's surface around a building. When you have buildings or trees or other obstructions, they tend to slow down the flow of air, and it slows down the wind. Compared to a building that was situated next to a large open body of water, there's nothing really to slow the wind down. So all things being the same, something with less rough exposure is going to be exposed to higher design wind pressures than one located with a lot of obstruction, the middle of a forest or the middle of a city. So we approximate this condition with these exposure categories. Exposure B, that's our roughest exposure, and the most common exposure throughout the U.S., but this is urban, suburban, wooded areas. Our exposure C category, which is our default exposure category, as we'll talk about in a few minutes, this is more open terrain with scattered obstructions, soccer fields, big parking lots, something of that nature, right? Exposure D, these are basically water surfaces down here in Florida, because we don't have any frozen ice in Florida, but it's water surfaces, and that's our smoothest exposure. So if you take a building, for example, this one here with just a mean roof height of 30 feet, and what effect does the exposure category have on the design wind pressure? Okay, well, it has a big effect. If we take the same building and let's say first it's located in some type of wooded area, a heavily forested area, so that it qualifies for exposure category B, and we do the calculation, and it's the design pressure on the windows and doors are 30 psf, just for example. Okay. If we decided one day, well, we're going to, cut down all these trees and sell them for a profit, and then now we have an open terrain type exposure, and we qualify for exposure C, the design pressure for that case increases from 30 psf to 42 psf. And then if we take it a step further and we say, well, we want the same building, exact same building, and all other things being equal, and it's near a large body of water, so that qualifies for exposure D, then the design pressure for that case goes from 42 psf to 50 psf. Okay, so compared to exposure B, it's more than a 50% increase in design wind pressure. So the exposure category has a has a pretty big impact on what the design pressures are. Okay. We all, wind speed gets all the attention. We talk about wind speeds when hurricanes are approaching. We categorize wind speeds and tornadoes based on damage, but things like exposure and size and location on the building, all these things affect what the design pressure is, and that's ultimately what's going to affect various products or how the building is designed. Okay. But the exposure category is a big one. So let's dig a little further. Exposure categories, and again, for the next part of this discussion, we're gonna stick to residential, because there's exposure categories differ a little bit based on what the height of the structure is, as far as how far the upwind surface roughness has to be. So just for simplicity, let's say we're dealing with residential. Buildings 30 feet and less in height. Okay. So to qualify for exposure category B, your building has to be surrounded by urban, suburban, or wooded terrain that extends for 1,500 feet in all directions. Okay. That's the base case for exposure category B. You have to have that to qualify for exposure category B. So if we look at this picture here, just picked a building in the middle of this subdivision or this area. And if we look in all directions, we can see that we have trees and buildings for 1,500 feet. And I used Google Earth to make the measurement. That's an easy way. Exposure categories, once you become accustomed to using Google Earth and the measuring tool, you can identify the exposure category pretty easily. Google Earth makes it much easier than what it used to be. But so just pulled the measuring tool across various directions from this building here, and so we clearly had 1,500 feet in all directions. So this building would qualify for exposure category B. Okay. For exposure category D, these are, again, dealing for residential single-family dwellings. These are buildings that are located within 600 feet of a body of water that extends for at least 5,000 feet. Okay, so you would, for example, here, these buildings located on the beach, the ones that are within 600 feet of the edge of the water, they're going to qualify as exposure category D. Now, that would also apply to inland lakes. I showed this example here for the Gulf of Mexico, but like you can see that lake up to the top left of the picture. If we took our Google Earth measuring tool, I think in one direction we'd have somewhere close to 5,000 feet. And if you're within 600 feet in that direction, you're going to qualify as exposure category D. Okay. So the exposure B, you have to have a certain amount of roughness around it. And exposure D applies if you're located near a large body of water with at least 5,000 feet of water exposure. If you don't meet any of these conditions, then you default to exposure category C, which is kind of, as we saw earlier in the design pressure comparisons, is kind of the middle of the pack. Exposure B, lowest roughness or lowest design pressures, highest roughness. Exposure D, lowest roughness, highest design pressures. Okay, so here's an example of of exposure category C. Okay, so you have to look at each building specifically. You can't look at an area and just say, this area looks like exposure category B, okay, or exposure C or whatever. You have to take your individual building and look in all directions. And like I said, using the Google Earth measuring tool or some other tool similar to that, measure out 1,500 feet from the building and see if you qualify as exposure category B. Okay, so for this example, this building that we're looking at here, it's where the yellow arrow starts at. We're not exposed. We're not near a large body of water. We are near a small body of water. But if we used our measuring tool, we'd see that it's not 5,000 feet. So we're not going to be in exposure category D. If we pull in some directions, we could qualify for exposure category B. But then we look in the direction that yellow arrow is pointing, and clearly we do not have trees, buildings, or urban or suburban type setting in that direction. So that building there, while it's located in a neighborhood, because it's near this golf course, it's going to qualify as exposure category C. Okay. So like I said, the important thing is that you don't look at these exposure categories as areas. You look at them, you look at a specific building and make the measurement from all directions. Okay. All right. And I see there are some questions already coming in from the Q&A. I promise you we'll have time at the end of the presentation to answer some of those. So, and lastly, on exposure categories, won't go in this in too great a detail, but the important thing to remember is that regarding this particular slide, what we're trying to point out here is that there's a transition from exposure D to C to B. Okay, as long as you stick with that I have to have 1,500 feet in all directions for exposure category B, you'll be fine. But exposure D doesn't immediately end and exposure B starts. Like for this example, for the mean roof height of 30 feet and less, exposure D would apply in the first 600 feet. And then maybe you have a lot of trees and a lot of other buildings, which looks like exposure category C, but you can't immediately qualify for exposure B because you don't have the 1,500 feet. So in other words, you would have to go an additional 900 feet so that you had the full, I hate to do this because it's going to slow down my thing, but you have to have the full 1,500 feet, 900 plus 600 to qualify for exposure category B. Okay. This is an example I was telling you earlier how it's different for different mean roof heights. If your mean roof height exceeds 30 feet, exposure B extends 20 times the height of the building, not a base 600 feet. Okay. All right. So let me get rid of these things and see if I can move forward here. All right. So let's talk about I mentioned the change to the windborne debris region. And many of you probably have heard of this. And we did the on-site classes back in September. We had there was a lot of interest in this topic. Okay. There was a change in the 8th edition 2023 Florida Building Code and still in ASCE 722, and it's in the I codes. And essentially what the change did was didn't really shift the windborne debris region by wind speeds. It changed, in that 130 to 140 range, it changed what areas qualify. Okay. So historically, since the inception of the windborne debris region, which goes all the way back to an appendices in the standard building code back in 1997, I believe it was 1998. We've had two triggers for the windborne debris region. The two triggers we have now are if your wind speed is greater than 140 miles per hour, you're in a windborne debris region regardless. You're automatically qualified, regardless of the proximity to the coast, to water, to anything. Wind speed greater than 140 mile per hour, then openings have to be protected. Historically, for that 130 to 140 trigger, historically we've identified it as areas that are within 1 mile of the coastal mean high water line. Okay, so it clearly kind of indicated it was kind of coastal areas. However, a group at ASCE 7 felt like this needed clarifying, and it did. The term coastal mean high water line, it's not a mapped or defined term. It's not defined in the code. Some have argued, well, in Florida, we do define coastal. We do, but not for the purposes of what this is. And it's not defined in other areas of the country. The key thing that we're trying to do was kind of clarify how the you apply the windborne debris region in that wind speed range, the 130 to 140. Okay, but it surprisingly, to a lot of people, it expanded the windborne debris region significantly, and I'm going to show you some examples in a few minutes. So as a result of that, Florida has effectively now at this point reverted back to the old definition in the 7th edition Florida Building Code building. Okay, this became effective August the 19th of 2024. So we're back to using what we were in the 7th edition and what we've used historically. The term coastal has been added back in. The reference to the exposure D we're going to talk about in a few minutes. All that we're windborne debris region applies like it has for the last 20-something years in Florida. Okay, in terms of that region. Now, I will note that the Building Commission did fund a study to look at the risk of windborne debris region in these inland areas that this change impacted. Supposed to get an interim report sometime in December and a final report in June of next year. Likely what's going to happen is there's going to be some adjustment to the windborne debris region for the next edition of the code. We don't know what it's going to look like. We haven't seen no one's seen the study yet. Study is not finished, and it's got to go through the code development process. So it will likely, I'm guessing it's going to be somewhere. We're not going to go back. We're not going to stay with the historical definition. We're going to go with something in between, is my guess. I don't know what that is at this point, but the group that's doing the study is also involved with ASCE 7. So likely this change will whatever is decided in Florida will likely filter into the 2028 edition of ASCE 7, which is going to be the next edition. And like I said, will also occur in the 2026 9th edition Florida Building Code. But let's just kind of look at it real quick and just kind of understand the implications. So on the surface and on the face of it, it looks like a minor change. We deleted the term coastal and then added in a language where an exposure D conditions exist upwind at the waterline. And the wind speed is greater than 130. Okay, so it's just that zone that between 130 and 140 where this change affects the windborne debris region. But by deleting the word coastal, okay, so that brought in non-coastal areas, so inland bodies of water, and then adding the language where an exposure D conditions exist meant that, you remember exposure D, and this is one of the reasons we talked about exposure D. That's where you have 5,000 feet of water exposure. Okay, so now any inland body of water, take some of the big lakes in Florida, Lake Apopka. And there's lots of them. It's more than just a couple, but Lake Apopka, everybody's familiar with, or at least heard of it. And it's a big lake. I think is in some places around 17,000 feet across. So clearly meets the exposure D condition. It's in the middle of the state. And at the beginning of the year, every building within a mile of the water line of Lake Apopka was now in a windborne debris region. Okay, so that was very different than how we had defined this region before, and quite honestly, a lot of people did not. We didn't really understand, when this change went into the Florida Building Code, we didn't really understand the how many inland bodies of lakes there are in Central Florida that meet that criteria, and there's a lot of them. Okay, but here's a quick coastal example of how this would apply. So clearly here let me get this annotate button going again. So clearly here along this coast, right? Okay, this is the Panama City area. Wind speeds greater than 130, but a little bit, but less than 140 in a lot of these areas. So we've clearly got 5,000 feet, and we have 1 mile inland windborne debris region, right? I don't think there would have been any arguments about that at all. But where it wasn't really clear is where you have these bay areas like what we've shown through here. Okay, and what this change was really intended to do was to say that, well, if you've got 5,000 feet of exposure, water exposure, which you do here, 1 mile from here is in a windborne debris region. That wasn't clear before. And jurisdictions were enforcing it in a variety of different ways. Okay. So, we were looking at this as it was coming through ASCE 7 in the code, seemed to, make good sense. Yeah, that's a good way to clarify it. What we didn't appreciate was like I said, the number of inland bodies of water. Let me get rid of this. Number of inland bodies of water that it was going to impact. Get the slide going here. Like I mentioned, Lake, that was another example I was showing you there, but let's get this. There we go. This is Lake Apopka, okay? Middle part of the state, wind speeds in between 130 and 140 miles per hour. Clearly got the 5,000 feet of exposure in a lot of different places around this lake. So within 1 mile, these areas at the beginning of the year were now in a windborne debris region. Okay. But what's not as obvious, is all these other lakes, these lakes over here, kind of bottom left. All these lakes here have 5,000 feet. Doesn't look like it, just glancing at it, but if you pull the Google Earth Ruler tool out, they've got 5,000 feet of exposure, a number of these. We counted, I think around 60 something lakes. And we didn't get all of them, but there are 60 something lakes, and the Florida Home Builders Association got a similar count, stopped counting, that met that criteria just in Central Florida. And then you have some in some areas of Northeast Florida, and then there are some areas in the Panhandle as well that met this trigger. So it was a much bigger deal than what everybody expected. So as a result, the commission decided to delay. I think is the phrase that they used, delayed the implementation of this and revert back to the old edition. And like I said, perform a study to determine the risk of these inland bodies of water to windborne debris. And it looked like when Hurricane Milton was approaching Florida with the high wind speeds that it had at the time, it looked like we might get a chance to evaluate that, because its path was headed directly across Central Florida. But as you all know, the wind speeds from Milton, ultimately wound up being a lot lower, much less than design level, and particularly in the central part of Florida. But stay tuned for that study and some changes to the Florida Building Code next round. But just so you know, the 2021 IBC and IRC and the 2024 IBC and IRC include that change from ASCE 7. Okay. So other areas of the country that have adopted the 2021 I codes, that change to the windborne debris region will be applicable. Okay. All right. So let's talk about our next topic, which is, and I won't spend a whole lot of time on this, but I don't want to get too deep in the weeds, but one of the more, what we thought at the time, substantive changes to ASCE 7 22 was a reduction in the roof pressure coefficients, which would result in lower pressures on the roof. ASCE 716, there was a drastic increase in design pressures on roof for steep slope roofs, particularly over ASCE 710. It's something that I've heard a lot of the wind researchers talk about for many years. This was something that needed to be done. I mean, going all the way back to ASCE 705, and then this analysis of all the different data was done. But the changes were pretty complicated. We had some significant increases in roof pressures, and there were multiple new zones. It was very complicated over what we had before. In ASCE 722, we've reverted back to the 3 roof zones. and all the pressure coefficients are truncated at 10 square feet and revise the roof overhangs, roof overhang loads. But the bottom line is it's a lot simpler and loads have gone down a little bit. They haven't gone down as much as they went up, but they have gone down a little bit. So just a quick example. This is for gable roofs, 20 to 27 degrees. As you can see, in ASCE 716, we had multiple new zones: 3E, 3R, 2N, 2E, just on and on. And historically, we've only had three. In ASCE 722, on the figure on the right, we're back to our three zones: 1, 2, and 3. 1 being the field of the roof, 2 being on the edges, and 3 being in some of the corners, not all of them. And the pressure coefficients, again, let me pull my annotate tool up here. This is just one example here. These pressure coefficients directly affect the design wind pressure. So as you can see, this is also for gable roofs of 20, 27 degrees. So if we look at our smallest effective wind area, which would be governed by would govern roof fasteners, connection of the roof deck to the framing. In ASCE 716, this number 3R, which is near the ridge, was 3.6, negative 3.6. And then if we look in ASCE 722, that's been reduced down to 3.0. So a pretty decent size decrease there for this specific condition. But again, one of the major the key changes is the simplification of the graphs and the figures. Now back to 3 zones instead of multiple zones. All right, let's. Same thing with hip roofs. I'm not going to spend a whole lot of time on this, but again, the simplification of the zones and the simplification of the log graphs where you determine your pressure coefficients. ASCE 716 for hip roofs from 7 to 20 degrees. We had 2 different graphs, and they were based on different geometries of the buildings. Very complicated to figure out what your pressure coefficient was. Now in ASCE 722 on the right, back to what how it used to be portrayed, and much more simpler, and design pressures overall a little bit lower. Okay. So this table here kind of gives you an example of some of the changes that in terms of design pressures, and you'll notice that for the lower slopes we see some decent decreases in design wind pressures for various zones, but where we see some of the biggest changes are for steeper slopes and hip roofs, for slopes from 27 degrees to 45 degrees for hip roofs, even a 21% decrease. So overall, a fairly decent decrease in design wind pressures for steep slope roofs over what we had in ASCE 716. Okay, I just wanted to mention this because this was the major issue with ASCE 716 and resulted in a lot of confusion in the International Residential Code as it didn't fully adopt ASCE 716, but that's been addressed now with the update to ASCE 722. Okay. All right. Next topic I want to talk about is tornadoes. All right. I would love to, if we had in the on-site classes, can ask people to raise their hand if they've know anything about or have heard about ASCE 722 and the Florida Building Code now requiring design for tornadoes. And a lot of people have not. Okay. It is some brand new provisions in ASCE 722. ASCE 7 has historically not addressed tornadoes, not addressed them at all. And the commentary gave people some guidance on where to go, where you could go, and there were some documents there for the Nuclear Regulatory Commission that it recommended. In ASCE 716, we did add some tornado provisions to the commentary, some guidance on how to design for tornadoes. The reality is there's this is a new field. There's a lot to be learned. There's a lot we still don't know about how tornadoes affect buildings. We seem to have a pretty good idea of what the wind speeds are, although we base wind speeds in tornadoes off damage, not off anemometers or anything that we measure. We base wind speeds in tornadoes off of damage. That seems to closely align or somewhat align with the damage we observe in hurricanes, where we do have measurements, and other windstorms. Okay, so we feel like there's some confidence there. So there's a lot of research going on right now surrounding tornadoes and how do we design for tornadoes. So we're going to talk about what's in the code, and you know, it's not as bad as what you might think, as you'll see as we go through this example. A couple of key things. It only applies to risk category 3 and risk category 4 buildings. Right? Okay, it does not apply to risk category 2. It only applies to buildings where the risk of substantial loss of life is high, which is risk category 3, or to buildings that are need to be operational after an event. Okay, so that's the key part here, is that it only applies to those two structures. And we in ASCE 7 and in the Florida code, we really just have a reference to chapter 32, and it's 1609.5 here. There's also a reference in the high velocity hurricane zone that just says that the design and construction of risk category 3 and 4 buildings have to comply with chapter 32 of ASCE 7, except as modified by this code. And there are a couple of modifications don't affect the design, but they're really clarifications related to tile roof design. So I'm not going to get into that. But in ASCE 7, there's new tornado hazard maps, and there's new design criteria. Okay, there are some exceptions to tornado design. One is that you have to be located in the tornado prone region. Okay, so if we go look at the tornado prone region, and usually when I show this slide, everybody starts laughing because clearly the tornado prone region is not a huge benefit. As we can see that about 3/4 of the country qualifies as the tornado prone region. So in Florida and the central and eastern US, this really doesn't help you at all. Okay. One thing I wanted to point out before we get into the other exceptions is that you need to understand what you're getting when you design buildings for tornadoes in ASCE 722. Okay, these are not storm shelters, and they are not going to function as a storm shelter. There are a number of notes in ASCE 7 that state this, that point you to the fact that if the code requires you to have a storm shelter, or you're designing a storm shelter, it has to meet the requirements of ICC 500. That's going to give you a design level for a storm shelter, and that's where we're looking at missiles that are 100 miles per hour, wind speeds up to 250, depending on where you're located. Okay, so these provisions do not qualify as storm shelters. What they're intended to address is, for lack of a better term, the garden variety tornadoes, right? Okay, the ones that the most common tornadoes, the EF2, EF0 to EF2 intensity, right? So these are wind speeds up to, I think EF2, the upper bound is like 138 miles per hour, somewhere in that range. That's what we're targeting. Okay, we design buildings in Florida all the time for 138 miles per hour. Okay, so kind of the thought is, then we ought to be able to economically design these buildings in other parts of the country and in Florida, where it applies, for these level of wind speeds. Okay, so these are not when we look at the tornado maps, these are not the EF5 level wind speeds or tornadoes, the ones that get all the attention. I believe seen a few studies that are statistics that close to 90% of all the tornadoes are EF2 and less. Okay, and even when you have these large tornadoes, the further you get away from the center of the tornado, the lower the wind speeds are, just like what we see with hurricanes. Okay, so let's start looking at some of the provisions. All right, First, let's talk about exceptions to tornado design. So we already talked about the first one, buildings outside the tornado-prone region. Obviously, that's not going to work in Florida. But if your tornado speed is less than 60 miles per hour, you don't have to consider tornadoes. Okay. Also, if your tornado speed is greater than 60, but if it's less than a percentage of your normal wind speed, then you're also exempt from tornadoes. So, for example, let's say you're looking at a building that's located in exposure category B. Your tornado speed is 60 miles per hour, but let's say your hurricane wind speed is 140 miles per hour. Okay. Well, then half of your normal wind speed is 70 miles per hour. So that exceeds your tornado speed. So you're exempt from tornadoes. Okay. And you have similar percentages, 60% for exposure category B and 67% for exposure category D. Okay. And the reason you see a little bit higher percentage for exposure B, C, for exposure C, and then again for exposure D is because the profile that we design, wind profile in a tornado is we design for it to be vertical. So there you don't consider exposure categories in tornado design. Okay. So the other big difference, and I'm going to show you the tornado maps in just a few minutes, but the other big difference is the tornado speeds they're based on the size of the building. Okay. Because tornadoes, compared to hurricanes, their size is relatively small, particularly compared to hurricanes. And so the size of your building affects your risk to a tornado strike. Okay. So what you have to look at, and it's not the floor area, it's the effective plan area. So what you would do, and I'm not going to get into a whole lot of detail about this, but you draw a convex polygon completely around the building. Okay. So for this example here, this is a U-shaped building, and it clearly has less floor area than the building on the right, but the effective plan area, when you draw the convex polygon around, is the same as this one. Okay. So these two have the same effective plan area, and for all practical purposes, if they're located next to each other, have the same tornado speed. Okay. So it's a little different than how we've historically deal with wind speeds, but the tornado maps are similar. Okay. So let's take similar to the hurricane wind speed map. So let's take a look what some of the maps are, and with a focus on how it impacts Florida. Okay. So this is our risk category 3 map, and this is for an effective plan area of 2,000 square feet. Okay. So as we see here, effective plan area, 2,000 square feet, risk category 3. There we go. Our tornado speed contour is 50 miles per hour. So everything outside of this is, everything outside of the 60 mile per hour contour is exempt from tornado design. Okay, so all of Florida is exempt from tornado design when your effective plan area is 2,000 square feet. Okay. All right, now if we bump up the size a little bit, 100,000 square foot building, again, risk category 3, but the 60 mile per hour contour is located along in here. So all of Florida is exempt from tornado design. Not all of Florida, but all buildings of risk category 3 buildings of this size. Okay. And if we can, there are 8 maps. I'm just showing you a couple of them. Okay. Then if we bump up the size to 1,000,000 square feet, and when you're in between some of the areas, you would design for, you could do an interpolation. For 1,000,000 square feet risk category 3 building, clearly tornado design comes into play. Okay. Same kind of thing with risk category 4. If we move risk category 4, 2,000 square feet, we can see that Florida is still exempt from tornado design. But then if we go to 100,000 square feet, all of a sudden it's greater than 60 miles per hour throughout the state. Okay. So we would have to consider tornado design for a risk category 4 building that was 100,000 square feet. Actually, some less than that, but you'd have to interpolate between the maps. Okay. All right. I am getting close to the end, so I want to kind of finish up on tornado loads, and I want to show you make sure we get to talk about the app a little bit. But couple of key things about the tornado loads is if they apply, you'll have to check. They'll have to be checked even if the tornado speed is less than the design wind speed, because a lot of the factors are a little bit different. The internal pressure coefficient, there's a vertical component that comes into play. So even if your tornado speed, let's say is 70 miles per hour, and your hurricane wind speed is 120 miles per hour, there's still the possibility that the tornado loads could govern for some conditions. Okay, and you have to design for the worst case. You could have a building that the hurricane wind speeds govern all the lateral, vertical components of wind design, but the tornado might govern only the main wind force resisting system vertical design. Those are all possibilities. Okay, so they'll have to be considered. If you have to design for tornado loads, there's a chance they might control. Okay, and again, I know we've talked about a lot here, but I'm going to have some time for questions, and I'll stick around afterwards. I want to introduce you to this application that Anderson has created, and it's a really slick application. It's free to use. The website is, I've shown it here in blue, windy.andersonwindows.com, and you'll have to sign up, but username and password. But it's a free tool, and we'll do a couple of things for you. You can do a simple wind speed lookup, like the one shown on the left. Calculate your wind speed. It'll also calculate a window and door design wind pressure for you. You just put in the inputs, what the key parameters are, and then it'll also allow you to do a project if you want to look at an entire building and build a project around what the design pressure would be required, because we know that design pressures are different in different parts of the building, whether it's located near zone 5 or located within zone 5 or zone 4. And then also for buildings, this works for any height building. It works. It's not just buildings less than 60 feet in height. It works for buildings greater than 60 feet in height. So we know that as the height increases, design pressures increase on all components, not just windows, but specifically windows we're talking about here. All right, so I'm going to jump over to the app, and I'm going to show you how to use it. So I'm on a different page here. Hopefully everybody can see it. Put in my credentials. I had already signed in, but it looks like it signed me out. So let's sign in. And like I said, you can pick, you want to just get a wind speed for the site, or do a design pressure calculation. Let's, because of timing and where we are, let's just do a quick design pressure calculation. And I'll show you how it compares to the code as well. All right, so let's pick this area in Florida, 17,362. Oh, it's already populated it for me. 17,362, and then we'll need to pick what ASCE 7 edition for Florida. We're going to be using ASCE 722. We'll need to pick our risk category. Let's do risk category 2. Assume it's a single family dwelling or some kind of office building, and then pick our exposure category. Let's say B for this example, and our mean roof height, let's say 30 feet. For a typical single family dwelling size. And then let's look at the smallest effective wind area, 10 square feet. Okay. So those are the parameters that you need to put in to calculate any type of pressure for a window or a door, and we'll click calculate. and we get our results. We see that our wind speed for this area is 140 miles per hour, and I picked this site so I could get a wind speed, of specifically 140 miles per hour, because I want to show you in the simplified table in the code. So for this side, our wind speed is 140 miles per hour, and then over here to the right, we get our design wind pressures. Positive for zone 4 and 5 is roughly 21 pounds per square foot. And then our negative for zone 4 is nearly 23 PSF. And for zone 4 and around 28 PSF for zone 5. And then also, if you look down, it gives you all the parameters that were used to do this calculation. The pressure coefficients, the internal pressure coefficient, velocity pressure coefficient, topographic factor, and the directionality factor. So you could verify the calculation easy. Okay, so just to show you, if we took this same building and let's say we wanted to compare it to the simplified table in the Florida Building Code. If we go, so we said we had wind speed of 140 miles per hour, and we have exposure category B, mean roof height of 30 feet. So if we go, let me stop sharing and reshare so you can see this. All right, so this is an excerpt of that simplified table in the Florida Building Code. Let me get my annotate tool back up here. So we said this is one option you could use for a simplified method for getting design wind pressures for windows and doors. So we said our wind speed was 140 miles per hour, which is this column here. We said we had a mean roof height of 30 feet, so we don't have to adjust it with the other table. And we said our effective wind area was 10 square feet. 10 square feet. So if we go across here and we look, we see for zones 4 and 5 positive pressures around 21 PSF, which is exactly, I'd say exactly within rounding. It's very close to what we got using the app. And then for the negative pressure zone 4, almost 23 PSF, lines well with what the calculation, and then 28 PSF for the negative in zone 5. Okay. The nice thing about it is if you're using using the simplified table in the Florida Building Code, not if your wind speed, let's say your wind speed is 118 miles per hour. Okay. You'll have to do an interpolation between these columns. This app will do it all for you. You do not have to interpolate. Also, if your mean roof height is something other than 30 feet or a different exposure category, you'll have to go down to the adjustment table, which is here, and you'll have to make an adjustment to the design pressure. So it's a little bit more complicated. The application does all of these things for you.
Hey, Eric.
Yeah.
Sorry to interrupt, but
yeah.
your presentation was supposed to end at 12:25.
That's
So
right.
technically we're on a break, but I think if everybody's going to be getting their lunch or doing whatever they're going to do, we don't start back until 12:45.
Okay.
So I think you're okay to, if you want to just try to go ahead and answer some questions, or you're also welcome to go backstage and you can answer them there.
All right. Why don't I answer a couple of them, because it looks like there's only 6 of them. Instead of typing them up, I'll just answer them real quick. Is that all right, Wendy?
Yeah, just everybody, if you're still listening, he's going to go ahead and answer some questions, but we are going to try to stay on schedule. So the next presentation does start at 12:45.
Okay.
Okay.
So, all right. Thanks, Wendy. Sorry about that. I was looking at the time and failed to look at it the last couple of minutes, but one question was define what a large body of water is, and I think we talked about that. That's a body of water, in the context of the windborne debris region and the exposure D category. That's where you have 5,000 feet of exposure to water. Okay, so Gulf of Mexico, large body of lake. Use that Google Earth tool. and you can measure how far that body of water extends. And if it's 5,000 feet, that's considered a lot, what I'm calling a large body of water, and will trigger exposure D category addition, and would have also played a factor in the, I say would have because Florida didn't keep that change, but the windborne debris region. All right, can you explain how to get from ultimate wind speed to design pressure for windows and doors? Okay, ultimate wind speed, to get to an allowable stress design for level for windows and doors, you can do one of two things. You can take the ultimate wind speed and multiply it times the square root of 0.6, or you can take your design pressure, just calculate your design pressure using the ultimate wind loads, and then multiply it times 0.6. And I'm glad you brought this up, because this windy calculator already does that for you. Okay, it gives you an ultimate design wind speed, but the pressures have already been multiplied by 0.6 to give you an allowable design level. So it works with the design pressures that are specified through the windows are tested for, and that's on their labels, which are those ASD level pressures. So it already does that for you, but there are a couple of ways to get there. But if you use the app, you already get there. How does being on the edge of a golf course, would that change you to exposure C? It depends. For that example that I gave you, it did. It all depends on what the surface roughness is next to that specific building. So you just have to look at that building individually. It's not specific to a golf course, but golf course is a good example of how it could affect the exposure calculation. What was that website from Anderson? It's on the screen right now. I think my screen is being shared. It's Winde, WINDE.AndersonWindows.com. Probably can Google it, and you'll also it'll also pop up. Is the IBC the best source for obtaining a copy of the 8th edition Florida Building Code? No. We talked about that early on. The Florida Building Code is not completely aligned with the International Building Code, particularly the 2021 and the 2024. Best source would be and maybe you're asking for ICC, and if that's the question, yes, the ICC is the best source for getting the Florida Building Code, but using the IBC is not a good source. Okay. How can we get the Winde application? Just go to that website. I think Crystal or someone has typed or pasted the link into the question and answer box. Like I said, feel free to reach out to Winde or Crystal or somebody at AIA Florida. If you can't find it or have a problem, feel free to reach out and let us know, and they'll get in touch with us, and we can send you the live link. Other than that, I want to thank everyone. Apologize for going over, but do appreciate your